All right, now we are ready to state the definition of a manifold. So an n manifold, or so here n is the dimension of the manifold. So this is the dimension. Dimension of M is n. It is a Hausdorff topological space with a countable basis such that each point has a neighborhood homeomorphic to the unit open ball in Rn. Right? So if n is 2, then we have a surface. So every point of so we have some x, and every point of our x has a little neighborhood that looks exactly like an open disk. Now, very common question is, why do we want to assume that it has a countable basis, right? And why do we want it to be Hausdorff? So it is a topological space, but it not just any topological space. So it cannot be something like the integers with arithmetic progression topology. So it has to be countable. Well, okay, arithmetic progression topology is probably not a good example, but it cannot be something like the cofinite topology, right? So it has to be Hausdorff. Now, so I'll give you two examples showing why these two assumptions are really important. Now, if you consider the plane R2 with the vertical interval topology, right? So here the basis is consists of those open vertical intervals. Then each point has a neighborhood homeomorphic to an open interval, right? But at the same time, so if we did not require our x to be second countable, to have a countable basis, right? Then we would have to call such an x a one-dimensional manifold. But probably it's not really a good idea, and because you know, our x is just bigger than a one-dimensional manifold. It's like two-dimensional. It is an uncountable union of lines. So this is why we do not really want to call it a one manifold. Now, to be honest, this example is probably not very good because this x is not uh, connected. So this x is not connected. So this is just the uncountable disjoint union of straight lines. But there exists a much more complicated but connected and path connected example of this sort. It's something that is locally homeomorphic to an interval, but we don't really want to call it a manifold. It's called a long line. Long line. So you may just go to Wikipedia and read about the long line in topology. So it's just this long line example is just harder to understand. But um, if you are interested, I suggest that you read a little bit about it and about its properties. So a long line is um, kind of similar to this example, but it is path connected. Okay, and the other example is about why we want our manifold to really be Hausdorff. So why don't we want to consider non-Hausdorff so-called manifolds, right? So imagine this, right? So imagine that we have two copies of the open two-dimensional disk. So let's place them in the 3D space on top of each other. So this is one disk, this is the other disk. So we have some kind of axis here, probably. So this is the disk with coordinates x squared plus z squared is less than 1 and z equals 1, and this disk is x squared plus z squared is less than 1 and z is 0, right? So this is my d and this is my second disk d prime, so they're exactly identical. Now we are going to glue together these two disks almost everywhere. So we are going to glue this point to this point, I don't know, this point to this point, this point to this point, almost everywhere except at the origin, right? So the origin, the two copies of the origin are not glued together. So then we're going to get this X as a quotient space of the disjoint union with respect to this gluing relation. And again, if you look at any neighborhood of any point in X, so there is a neighborhood that is homeomorphic to just the usual open disk, but still this something like this is probably kind of too strange to be called a manifold. So this is why we really want to require our manifold to be Hausdorff explicitly, because if we did not, then it would lead to examples that look like this, which essentially means that it would be impossible to classify our manifolds. All right, so then a one-dimensional manifold is, if it is path connected, then it is either a circle or a real line. I'm not going to prove this. I don't think it's very hard to prove, though. I don't really remember why I decided not to prove it, but I'm just given this theorem without proof.